Welcome to the empirical and molecular formula video. By the end of this video, you should understand the difference between an empirical and a molecular formula. You should be able to determine the empirical formula when given the molecular formula. And you should be able to determine the empirical and molecular formula from lab data. An empirical formula gives the lowest whole number ratio of the elements in a compound. The molecular formula, on the other hand, is the actual formula of the compound. This can be the same as the empirical formula. Sometimes it is the case that the actual formula is the lowest whole number ratio of the elements in the compound, but not always. Let's look at some examples of empirical formulas. Take hydrogen peroxide, H2O2. Notice that the ratio of hydrogen to oxygen is 1:1, so its empirical formula would be HO. C2H4 has a 1:2 ratio of carbon to hydrogen, so its empirical formula is CH2. C6H12O6 reduces down to an empirical formula of CH2O. Here's a few more. Pause the video here and see if you can predict the empirical formula given these molecular formulas. Welcome back. Here's what you should have gotten. Notice that both C2H6O and N3O2 are cases where the empirical and the molecular formula are the same. Let's talk about how to calculate the empirical formula. We can use experimental mass data to calculate these. We're going to break this down into a couple of steps. In step 1, you obtain the mass of each element present in the compound. Then you convert these masses to moles of each element. Then you determine the ratio of these moles to one another by dividing through by the smallest number of moles to convert it to a whole number ratio. Occasionally, you may be left with non-integer numbers, in which case you'll have to do step 4 and convert these to whole numbers. Let's look at this in practice. Here we're given a compound of aluminum, which is formed by the reaction of 4.151 grams of aluminum and 3.692 grams of oxygen. So, we've already completed step 1. The problem gives us the masses of the elements in the compound. Now we need to convert these masses to moles. First, aluminum. We know that 1 mole of aluminum is equal to 26.98 grams of aluminum. So setting up our proportion, we solve for x and find that we have 0.1539 moles of aluminum. Repeating this procedure for oxygen, which has a molar mass of 16 grams, we find that we have 0.2308 moles of oxygen. From here, we'd be left with a ratio of 0.1539 to 0.2308. However, you can't have a formula with decimals in it, so we need to convert these values to integers. I'm going to start by dividing through by the smaller of the two numbers. So, aluminum is the smaller value, so I divide my 0.1539 by itself to get 1. I do the same for oxygen, dividing 0.2308 by 0.1539, and I get 1.5. This gives me a formula of 1 aluminum to every 1.5 oxygens. We're getting closer, but we still can't have a formula with decimals in it. So we need to convert this 1 to 1.5 ratio into a whole number ratio. Here's where that step 4 that I said you may occasionally have to do comes in. It's pretty easy to see that to get to whole numbers, we just need to double both values. So when we double both values, it becomes a 2:3 ratio, or Al2O3. Sometimes the problem won't give you grams of each element in the compound, but rather it will give you mass percents. In this case, we're told that this compound is 25.9% nitrogen by mass and 74.1% oxygen by mass. This question can be solved just like we solved the previous problem. Since percents mean part of 100, we can pretend that we have 100 grams of this compound. It doesn't actually matter how much we have. If we just pretend that we have 100, that means we would have 25.9 grams of nitrogen and 74.1 grams of oxygen. Notice I'm literally just replacing the percentages with grams. From there, I'm just going to complete the same procedure I did in the previous problem. I'll convert my grams to moles using a proportion. So I find that I have 1.85 moles of nitrogen. Notice here I've used 25.9 grams since 25.9% of the compound is nitrogen. And assuming 100 grams, 25.9% of 100 is 25.9. Repeat this for oxygen. I'm given 4.63 moles of oxygen. Now divide to determine the ratio. So I'm dividing through by the smaller number, and I get a 1 to 2.5 ratio. Again, we can't have a formula of 1 to 2.5, so I'll need to double both values to get N2O5. Now let's talk about how to find the molecular formula. Recall that the molecular formula of a compound is either its empirical formula or a whole number multiple of the empirical formula. Here's two examples. Benzene has an empirical formula of C1H1 and a molecular formula of C6H6. Notice the molecular formula is a multiple of the empirical formula. Likewise for glucose. Here's the kinds of problems you'll see for this. Here you're asked to calculate the molecular formula of a compound whose molar mass is 60 grams per mole and whose empirical formula is CH4N. For these kinds of problems, you'll always be given the molar mass because you need this information to determine the molecular formula. So first we're going to calculate the molar mass of the empirical formula, which you're given in the problem. So I find that if I add up the molar masses of 1 carbon, 4 hydrogens, and 1 nitrogen, I get a molar mass of 30 grams per mole. Recall that the molecular formula must be some multiple of the empirical formula. So if we know that the empirical formula weighs 30 grams, we need to figure out what multiple of 30 gives us 60. You could probably do this in your head, but just in case it's a more complex problem, we'll go through the steps here. So we divide the molecular molar mass, 60, by the empirical molar mass, 30, to get 2. This means that the molecular formula must be double the empirical formula. So we can multiply our empirical formula by 2 to get C2H8N2. So our 1 to 4 to 1 ratio becomes 2 to 8 to 2 for the molecular. Here's an example to try on your own. Pause the video here and determine the empirical formula. Then, given the molar mass, determine the molecular formula. Welcome back. Here's what you should have gotten. We find that our empirical formula is ZnO because it's a 1-to-1 ratio of moles of zinc to oxygen. And since the molar mass of our molecular formula is 3 times that of our empirical formula, our molecular formula is Zn3O3. That brings us to the end of this video. Let's review our goals. First, we looked at the difference between an empirical and a molecular formula. Then we learned how to determine the empirical formula when given the molecular formula. Then we learned how to determine the empirical and molecular formulas from lab data.